Okay, we will get started soon. So first, let me introduce our next speaker, Professor Chuang Gan. Professor Chuang Gan is a faculty member at UMass Amherst and a research manager at MIT IBM Watson AI Lab. He was a postdoc at MIT and completed his PhD with the highest honor from Tsinghua University. So without further ado, let's welcome Professor Chuang Gan for his talk.
All right, so let's start. So I'm Chuang. So I'm a professor at UMass Amherst and also spent some time at MIT IBM Lab. And my research focused most on the computer vision and the robotics. So today I'm excited to give this invited talk and introduce our long-term effort to building the kind of 3D world model with aim that bridge the visual intelligence with the physical intelligence. Okay, let's start. I would like to begin this talk by inviting all of you to watch a video of my third-year daughter, Carolyn. So she's playing a popular game called Circle Puzzle. Despite we have never taught her how to play this game before, but we can still see that she has some basic knowledge about objects, how to interact with them, and then formulate a plan. Although sometimes she needs to reformulate her plan, but eventually she managed to finish this task very efficiently. The question I would like to pose is here: how could she succeed in this game? Studies from cognitive science and neuroscience have suggested that even the 3-year baby here has a common knowledge about objects and abstract knowledge about object affordance. Carolyn can also use her mental model to imagine what is going to happen next and plan her action accordingly. Since we are working on AI, a fundamental question I want to pose here: how do you think that the most advanced AI systems today have the intelligence of my baby Carolyn? One answer might be yes, because right now we have many intelligent robots that already can do a lot of tasks. For example, we have this kind of intelligent robot can unfold clothes using the airflow. We also have the kind of like a robot that can play the soccer as flexible as human. We also can use a large language model to do personalized, to have the kind of tidy robot that can do personalized household. We can even push more model that we can play this kind of throw and catch by arm play game. However, I will still say that we are still far from that kind of general intelligence, or we say the kind of physical intelligence. What do I mean by that one? So we can take a look for the most popular embodied AI system. This mobile Aloha system actually is built by the Stanford. Let's dig into the concept of what is the embodied general intelligence, or what I talk about physical intelligence. The concept can be very different from different person perspective, but I would like to put it in a more general way. So at least we want an agent that can perform multiple tasks, can take a multimodal instruction, and execute a diverse range of tasks across different environments. Now, let's take a look how this most popular mobile Aloha system can perform in terms of the generalization. You can see that you slightly change the object location, the poly will fail. So from this video, you see, even though you can do a lot of amazing demo that we see on the website, but in terms of generalization, it's still fall short compared with my baby Carolyn. So how can we achieve this kind of physical intelligence or embodied general intelligence as flexible as a baby? I think one way to achieve that one is building a world model. So basically, we have one route to get there that is by reverse engineering of human intelligence that work both in human brain and mind. So we also have heard a lot of words about definition of the world model. For example, people might say that a large multimodal language model can be used as a world model. But let's take a look about this example. So we can first ask GPT-4 a question that in these images, what will happen next? So it seems that they can imagine what happened next very good. That he said that the image show a hand appearing to drop an egg. Without support, the egg will likely to fall due to gravity and make breakdown hitting the hard surface below. It seems that he understands the gravity concept, right? That he can imagine what happened next. But how about we do one step further? Let me ask this question. Which ball will reach the ground first? Okay, maybe I do a test here. How many people think the right one? How many people think the right one? So how many people think the same? Really? So we can do a simple test because here is it have larger speed and also it has it's same distance. Actually, this will fall down first. Anyway, but we can see how ChatGPT will answer this question. He will answer that this ball reach the ground at the same time. That's clearly wrong. And he can also explain the reason. Because the only force acting to the ball is gravity, which puts them down with the same acceleration. The time it taken for object to fall certain working distance is independent of horizontal distance covered. So he talks some facts, but they're doing this kind of physics reading, they still make the mistake. So on the other hand, that I think the most popular word that's also about this workshop that we talk about is like large video model as word model. This might be true because when we see this kind of fancy video, we see that current video model already captured the common sense that as strong as the human. But how about we take a look of this video? So when we take when we take a closer look of this kind of video storage system, we find that there is a tremendous challenge for them to simulate fluid dynamics, perform collision detection, or even understanding the friction and capture the gravity. So there's a lot of physical common sense. Actually, lucky we are still far from there. All right. So how can we bridge the gap? How can we really model the world that understanding their physics principles? So in my lab, we have a long-term goal that trying to combine the power of generative AI with a term we call, and also another powerful tool we call as physics engine. And we believe that only combine the power of both of them, we can encode both the physics knowledge and the general power of the data. All right. So in today's talk, and in the first part, I will pretty focus on introduce a powerful tool called differentiable physics engine that enable us to collect large-scale 3D physical interaction data. Let's start from a very simple example. That by only taking out these images, I would like to put a question. So, which object carrier? How many people think the gray sphere? How many people think the Corinth sphere? And how many people think this confusing? No idea. Okay, probably this is true. But how about show you a video here? Okay, so how many people think the gray sphere carrier? Okay, most of you can answer the question correctly. So how can we achieve that one? Actually, we actually based some physics knowledge here. We know the moment, the conservation of momentum that we understand, that we trying to understand this Corinth sphere is actually the carrier, right? So basically, so when we do this kind of physics reasoning, actually our Mando, so we actually rely on our Mando simulation, or we call that the kind of world model to imagine what's going to happen when we adjust the physical parameter. How could we? So the next question is how could we enable machine to do the same? Here I will introduce a powerful tool our lab has been devoted for decades. It's called differentiable physics simulation. So what it is? Let's take into a concept of the physics simulation. Essentially, the physics simulation that in the forward simulation step, given the current state S and the system parameter, the simulator can compute the state of next step. And then by continuing running the simulator, we can simulate the whole physical process. So this is essentially the concept of physics simulation. And from that event, we are trying to estimate the physical parameter here. So how can we do that using the kind of physics simulator? The idea is pretty similar. So the idea is pretty simple. Is that we are trying to find, so we are trying to search an optimal parameter that can best simulate object trajectory that match the video observation. Essentially, if you find if you find the right physical parameter will simulate the video, it should be the same as the video observation. If this match means that you find the good, you'll find the right physical parameters. And how can we do that? We actually can define a loss by comparing the simulated object trajectory with the video observation. And the goal here, we're trying to minimize the loss and then getting the optimal parameter here. And the idea of differentiable simulation that we can, using, for example, the modern tool, DiffTaiG, we can make the whole physical process differentiable. Then we can, using the gradient descent as simple as training neural network to solve this problem. Let's give a concrete example. In the left, only using one reward battle video on the left side, we are trying to contrast the physics model of this battle table. You can see that using that kind of probe, we can very accurately model their collision parameters. This is the way that we're trying to understand doing the kind of physical reasoning. And you might be curious that how we can do achieve that kind of physics reasoning in much complex shape. For example, that kind of color rotor, hand, or even the soft body rod. So the idea here that instead of compare with the state loss, here we can actually render images from the state, and then estimate the physical parameter by comparing the random images and the observed images. We can define for them a perception loss in terms of the render images. And then it turns out that by measuring the difference between the estimated physical parameter by comparing the two images, you can get you can roughly guess the parameter. Use that way, we can build the kind of digital twin from the left side red world and to the virtual world to exactly reconstruct the action sequence and also physical parameter. And the whole idea here is that we try and combine the power of differentiable physics engine, differentiable rendering with the kind of perceptual visual comparison, and take a step that we can understand the physical intelligence here. And we can further make a push to simulate the both geometry and the physical parameter property. So one example I show here is that because in many periodical, you probably know the 3D geometry, but in some soft body scenario, probably you have no prayer of their geometry structure. And in that case, for them, we try to estimate the Young's modules of this toru, or with causality of this kind of drop it. How can we do that? The idea here is that by comparing different physics with neural rendering from multi-view images, we can perform the kind of physical reasoning of soul body from very flexibly. We can reconstruct both geometry and physical parameter, and the whole pipeline is differentiable. As a result, we can take a video there, reconstruct both geometry and infer physical parameter from multi-view video sequence. And the same pipeline I just introduced about the physics simulation can also very easily to be extended for the robotic planning to collect the physical interaction data. For example, we can simply replace the physical parameter here as action. So essentially, given state as an action, you can simulate the next step and control the whole physical process. This essentially is the embodiment of physical interaction data. And since this is a physical interaction task, or we call it a planning task, instead of measuring the loss, we are trying to receive a reward at each time step to measure how well the task has been solved. And again, the objective here that we're trying to maximize the sum of the reward from each time by finding an action sequence that can achieve the best reward, very similar to the reinforcement learning step. And since we have the kind of differentiable physics simulation, as I mentioned, the whole physical process we can write in a differentiable way, means that we can backpropagate the gradient and action sequence to find a solution. So we first apply this idea to the kind of cell body manipulation task. We're trying to collect the kind of large-scale demonstration data for cell body manipulation. And in each task, that the agent needs to use this kind of manipulator to deform or placing to a desired shape. Using a pipeline I just described, actually we found that it can be much more efficient to collect the demonstration data compared with the reinforcement learning. For example, the left curve plots the reward curve. We can find that the gradient-based physics solution in this green curve achieve a much faster conversion speed and earn much more reward in reinforcement learning. So when compared with reinforcement learning. We also provide a visual comparison here. So on the left side, our physics-based solution could find a solution with 200 iterations. By contrast, this can reinforce learning, even with training around 10,000 million episodes, they still don't learn anything. So this powerful actually enable us to collect large-scale physical interaction data for video generation. So we can also transfer the policy we learned from simulation to the real-world task, so I'm rolling, cutting, unrolling, and assembling. We also apply this idea to a wide range of physical interaction tasks. For example, here we are trying to solve a multi-material robotic cutting problem. The goal here is that we are trying to cut as much as volume and avoid collision with the rigid core in the middle. We can find that by using this kind of differentiable feed engine, we can optimize the beautiful trajectory to achieve this goal. We are also able to transfer the policy from the simulation to the real world that enable us to cut various kind of fluid with different rigid core in the middle, very robustly. Besides that, we have also built a kind of fluid lab that can support very complex fluid simulation, including elastic, plastic material, liquid, and gas. Again, we can also do that kind of interesting task in the real world. For example, we can make that kind of ice cream and also make it coffee latte art. Here's a more recent result. So our simulation already support that kind of photorealistic rendering that can simulate a bunch of thin shell manipulation tasks, so that we can manipulate the paper and also the cloth. To really, since 2 years ago, we are making a push to building a very general purpose differentiable physics simulation called Genesis, with the goal that to enable video generation from large-scale physics simulation. So Genesis is a large effort that's around 20 researchers from SIMU, MIT, a bunch of university professors, students actually deeply involved in building this kind of simulator. And with the goal that we really want to building a general purpose data engine for video generation with a tailor for the physical interaction data. And Genesis have a couple of key features that's not enabled in the existing physical simulator. For example, it actually supports both rigid and articulated body simulation, and also supports liquid, gas, deformed object materials, thin shell materials, granular objects, and most importantly, it supports their coupling, which enable that kind of large-scale physical interaction data that cover a wide range of material. We also support a wide range of embodiment, including robot arm, leg robot, Dr. 10, mobile robot, drone, soul body. We also we recently also support human interaction in the kind of simulator. So this simulator is hoping to make a release at the early of November. So with this kind of powerful feed engine on hand, the next question that enable that kind of video data generation is really about how we can get into the 3D eyesight, and how we can place the scene, how we can define the task. So in a recent work published on XML this year, we have a work called Robot Gen. The idea of Robot Gen that we're trying to enable the kind of to collect the physical interaction scale automatically. The idea is to marry the power of generative AI with the physical engine, and we term as a generative simulation. So the workflow of Robot Gen is as follows. First, it can use a large model to self-propose interesting tasks that the robot should learn to solve. And then, given the proposed task, it can generate the corresponding scene in the simulation. And finally, to really getting the physical interaction data that we can automatically generate the training supervision for learning this task. And then the skill learning will be learned automatically in the simulation. Let's take a concrete example. The first stage of RoboGen is a task proposal, which aims to generate a meaningful and diverse physical interaction task for embodiment to learn using large language model. For example, in this case, we can sample a robot. We can sample embodiment is a robot arm, and sample an object is a safe. RoboGen can generate diverse tasks that involve reasoning about the affordance and functionalities of the safe. For example, we can propose tasks: open the safe door, dispose document in safe, and so on. After the task proposal, the second stage is the scene generation. So condition on the generated scene, RoboGen first generating the component and configuration of the scene, which include the assets needed and their configuration, such as size and location. Then the asset can be retrieved from either existing dataset or using the advanced text-to-3D generation models. And when generating the scene, another step we need to verify the scene makes sense or not. Here, we're using a vision language model to verify the correctness of the retrieval asset and generated scene. With this procedure, actually we can populate and build upon the scene in simulation. Finally, after scene building the simulation, we need to answer the question how we can really collect the correct physical interaction data, which involve the task implementation, algorithm selection, and reward generation. The key idea here, we can use the large model to writing the reward function, writing object function, and then the problem can be automatically solved. With this powerful RoboGen pipeline, we are able to achieve that kind of function. Just one clip, give me any embodiment, you can generate endless embodied AI task and enable the physical interaction data collection at scale. All right. So as we all know, how we can gather the large-scale physical simulation to mimic that, to kind of understand how lack of the physical interaction for video generation. The next step is how we can really learning from the kind of physical interaction data and enable the video model or the kind of world model has some 3D and physical knowledges. So the first idea our lab has been working on is that we're trying to learning a world model from this kind of 3D interaction data. The idea is that when we have large scale that kind of 3D physical interaction from simulation, we can actually inject this 3D world data into the large language model. And this is essentially the idea of 3D LM trying to do. And the challenge here is two. First, how we can collect the 3D and language data. Second one, how we can design the framework to align the 3D video data with the large language model. So for the first step, actually we propose a large-scale 3D language pre-training data set. And the idea that we're trying to using the ChatGPT to with initial prompt, we can rewrite the caption to gather large-scale 3D language interaction data, which is enable us to build on top of language model and doing that kind of large-scale visual interaction tuning on top. So those, actually the method is pretty simple, that we can first getting the multi-view images, and then we can have a ChatGPT to generate the question, and then using VLM, such as ChatGPT to answer them. After several rounds of QA, we can actually ask GPT to summarize the answer and obtain a description of the scene. And then we can further we can do revision-based prompting for every question. We ask the GPT to rewrite, iterate, or reformulate its answer, and doing some question answering task. And with this 3D language data on hand, the interacting tuning can be relatively straightforward. But actually, the fundamental question, how we can actually obtain the feature of this 3D data. So our idea is that first, for any specified 3D scene, we start with rendering multiple images at various locations, and then we try to obtain the 3D features. So there are three types of methods for constructing the mapping. First, if we have the depth information and camera parameter of the photo, we can directly reconstruct the 3D space. And if not, we actually can use nerve or grassland on the 2D images to obtain this kind of 3D feature and getting this alignment. And finally, we can do this kind of 3D interaction tuning enable this large model to understanding the 3D physical interaction data and to do a bunch of tasks. And what 3DM actually can do, first, actually, you can give a 3D scene here. They can describe the 3D scene video into a decent way. For them, we can say there's a 3D model of small, old, and ruined castle with doorway and stars. Besides that, you can also do some fancy, they can 3D chat robot. For example, here, we can ask the agent that's trying to, so when we look at this 3D scene, sorry. So we can say, I want an icon on my suit. Could you help me to find this one? Actually, the agent will look around the scene and find that on the close count. And he also wants a tower. He will also look at the 3D scene and see where the object actually, this 3D object actually are located. Besides that, you can also do some task exposition in the 3D scene. For example, we give this kind of 3D images. We ask, I want to clean up the room. What should I do? This model will actually give you the step that you can first empty the trash can, pick up the cleaning solution, a spawn, and then clean the mirror with a spawn. So this large model can understand the 3D static scene. Another step as well related with this workshop, that how we can enable them to actively interact with the world that's through that kind of water model. So a way to achieve that is we're trying to building a water model of this one. The water model would be here. It's more like the capability to imagine the future, what happen next, and then they can plan action accordingly. So in a recent work that published in SML year, we show idea that we're trying to using the video as a word model for robotic imagination. For example, given this observation, and we ask a question, how to close the middle drawer? For a human, actually, we always imagine what will happen, how we can do that one. So using this robot dreamer, we can actually simulate the step and see how we can actually close the middle drawer. So for a video model right now, it's pretty good at doing this kind of single step imagination. But on robotic setting, the most important capability is doing the compositionalities. Let me show an example. So the idea here that we're trying to transfer the natural composition of language composition into the video generation, video diffusion process. As a result, we can achieve different composition. Even we have never trained on this composition, they can achieve that kind of I can generate the video of this new word composition. For example, if I choose the move spoon to the pencil can, you can see you can do that correctly. And we can try another example. We choose move spoon to the orange. And we see another example. So we say that we move the pencil scan to the orange. So actually, this kind of compositionality is the key. I think that the generation can be enabled. And the idea here, we're trying to during the training, we try and combine the different language composition scale into the diffusion process and enable the model actually doing the kind of compositionality generation. The next question is that how we can encode this kind of video imagination model with the 3D world model we have, the 3D align model. And the idea here that we first build it on the backbone on the 3DM, and we build the kind of 3D VLA framework. The idea that we're trying to enhance the model capabilities by, So we build the backbone on top of 3DM and further enhance the model capability to interact with the world by adding a series of interaction tokens. And next, we inject the Go imagination capabilities into this 3D VLA by first pre-training the embodied video diffusion model and employing projector for aligning the align with the diffusion model. With this goal, actually, we are enable the model actually to we give a long query. They can imagination go and apply action accordingly. So let's run a concrete example about what 3D VLA actually can do. So let's go to here. So actually, they can do this kind of Go imagination, recognition, localization, and given the question here, for example, can you help me to arrange my room? You'll say, okay, I can see the table in the middle. And then I can see what's in the middle. Actually, he can find that there's a tip over Coke and a misplaced spoon. And the question that can you put the spoon back into places? He said, of course. And he will think an imagination to go here. Okay, we should put on here. And then he will, based on the imagined goal and the input observation, he can actually plan an action sequence to achieve the goal. Let's give another example. So what if we upgrade the can? The model can imagine what it will look like about the goal. Okay, it will look like in this way, and then he will plan a trajectory to achieve this goal. So in this case, they actually were doing very similar to my baby Carolyn, that when he achieves a task, he first imagine what he can do about this object, and then plan her action accordingly to achieve the task. So this world model can not only be used for the single agent. In recent work, we also show that this video world model can also be used for the multi-agent collaboration. So in this case, we are trying to see that so there are two agents. They are trying to cooperate given partial egocentric model of the world. And for them in the TW Cook environment, they are trying to complete the task. For them, they are trying to cooperate, finish some dish according to the recipe. Well, there's only one cutting board there. So this agent actually needs to cooperate, imagine what other can do about this one, and then achieve this kind of cooperation. With video model as a world model, actually we can do this kind of task very straightforward, that we just have two agents and imagine the action outcome, what the other agent might to do. And then we can actually doing some tree search-based approach and enable two agents that can doing this kind of multi-agent cooperation task very flexibly. All right, so till now, most talk about that how this world model can be using as a world model for single agent and multi-agent cooperation. At the end of my talk, I will also talk some future direction I would like to working on. It's about 4D video generation. So the goal here is that given the input line and the reference images, we try to generate non-human video with natural camera shot change. So you'll probably see that for all the kind of video generation model, they're trying to achieve that. They're trying to only show the face. So some work might show a little bit of hands, but most of them about single camera. But when we really want to further making a video show here, actually it's composed of different camera combinations. For them, you can test close up, medium shot, and full shot, and wide shot, right? This is how you actually the director making that kind of video that kind of talk show. So in a recent work, we collected kind of speech card data set. Basically, we have collected the kind of filter human video with different camera shots, paired with correspondent with text, audio, 2D keep on, and 3D as and the 3D annotations. And again, we're using an LM actually trying to control the full process. Basically, we using large model, we understand, okay, given the script, what it should be the output of action, what should be output script, and actually they can also automatically control the camera shot. Here, I will show you a very preliminary result.
Pour que la plante puisse se développer et croître dans le sol pour nourrir les plantes. C'est donc un atout pour les plantes, mais c'est un fléau pour les sols. Et que le coût de l'énergie a fortement augmenté, entraînant avec lui une flambée que nous avions eu à mener. Alors, il faut être tous ensemble pour le relever. Mais l'agriculture a déjà connu des révolutions agricoles, 3 révolutions en 3 décennies, parce qu'ils ont des diagnostics de plus en plus précis. Mettre à quel endroit? Bah oui, on n'a pas un sol.
All right, so finally I want to acknowledge all the students behind the work and also generous support from funding agent. I think we still have some time for question answering. Thank you.
Okay, many thanks for the great talk. Any questions?
Thanks for your talking, Professor Gan. And I have a question about learning physics from differentiable physics simulator. I wonder how to scale it to large scale and open world.
All right, so the question is that how that kind of physics engine I introduced in the first part can scale to the much open and diverse open world. So this is actually a very good question, and also this is a fundamental research question I would like trying to address for a couple of years. I think we are thinking there's two major steps that actually can make the kind of model really scale. The first is our effort at building the kind of unified physics simulator. I think before we most doing that for it's also very common in the robotics community that they're trying to doing one task with one simulator. And this actually fundamentally hinders the process that how we can scale up. This is the motivation why we're building the kind of Genesis physics simulator. So for them, compare with most recent simulator like FXGym, the most focused on rigid body. But here we make a major step that we are willing to trying to solve different kind of, but a wide variety of tasks with different material coupling. So this is a fundamental thing we're trying to do. And the second thing is that it's all common for the robot simulation community that it's not really easy to set up a scene, which means that when we even you play with any modern simulator, that you have to handcraft the scene, finding a side, define the task, define the scene, are not really too easy to scale up. And in the robot gen and also follow-up work we haven't released yet, that we really trying to think is trying to how we can came from the real world distribution. For example, in a paper we actually just accept on the nearest, we propose a paper called Craft. We propose the idea how we can leverage the 2D diffusion model, leap into the 3D scene, generating very realistic photorealistic 3D scene and eyesight that from and automatically. So this is another step. We're thinking that we need to combine a powerful unified physics engine and the power of generative AI. That with these two content together, we think we can make some interesting and maybe also promoting progress to really scale up the physical data in simulation.
Okay. Do you think vision language model is a possible simulator?
Yeah. So I think vision language model might not be good really for creating scene and imagination about scene, but this essentially is the visual generative model trying to do because they learn a lot of real world distribution about how scene will populate, how objects are interact. But the visual language model can play a very important role for the scene verification. For them, using video model, image generation model, or large model to generate the scene, generate task. It's good to ask a vision language model to say, okay, whether it's correct or not. At this part, I think vision language model play an important role to doing the kind of rejection or the kind of verification. I think they can be used in that way, in my opinion.
Okay, that is using vision language model is very good for understanding.
Yeah, it's more about to understand the scene and also maybe can writing some reward function, enable the task learning stuff, the skill acquisition stuff. Yeah.
One more thing. Can I ask what's the difference between world models and spatial intelligence proposed by Professor Feifei?
So I think they are related in several ways. I think we also have some deep discussion in CPR, I think. So we both believe that for the next days, 3D, physics, and functionality would be the most important thing that for AI community.
Okay, thank you.
Thanks for the questions, and Professor.
Okay. Professor Chuang, I have a question. Would the first version of Genesis have the pack nerve features for nerve or GS-based simulation?
So the question that whether we will enable some learning-based rendering into the simulation, the answer is no. We are not there. But I think in the future state that we are trying to incorporate this 3D Gaussian splatting and also the nerve, that kind of large scene eyesight generation into the framework.
Any questions? Yeah.
Yeah, that's a good question. So the question is that the physics simulator we build most on the kind of places NPM, that kind of physics approach. And the question that whether we can actually just learning from the data, learning from real world data, and also getting the kind of purely neural physics simulator. Is that the question, right? Yeah. So actually, it's a good question. So we actually have been working on this kind of learning physics simulation for them using graph network. Or we can always building the kind of physics informed network that basically is still a PDE, but some components, for example, the consider law you can learn from data using neural. I feel that for the first time, just learning from data, that I think we have to do that one. I think it's okay when to learning from the state representation. For them, you're learning from particle representation. So there are a bunch of work trying to learning from the particle representation and learn using graph network to model dynamic. The performance looks okay, but I think it's still open question how you can learning the kind of physics simulation from pixel. So I think this is still a solved problem based on my knowledge. Of course, you can always learn this kind of video model, but as I showed in earlier, it's always hard to capture this kind of physical dynamics. And graph network actually has a good inductive bias that can capture some of the kind of physical relationship in an intuitive physics way. But unfortunately, most of this work will work only on the state particle representation, which is not really available. Or in other way, that the data we generate can be using for the for learning kind of physical interaction. But to my understanding, they are still most focused on learning one graph network for one material. It remains challenging that how you can building one unified model for all the kind of physical interaction. I don't think there's existing work right now, but maybe an interesting foundation model future work. I don't know. So, but I think a neural consider allows for them we probably on SML last year. So basically, you still a PDE, but it's well known, for example, the material model constitute is really hard to tune, really hard to mimic the real world distribution. In this case, that you have a PDE equation already here, and you have some result you're trying to learn it from data. I think that's a promising direction to go.
Thank you. Any other questions? Okay, if there's no more questions, let's thanks Professor Chuang Gan again.
Thank you.
Okay, sorry, I just entered the Zoom meeting. So